Bismillahirrahmanirrahim. Welcome student to the course of Electric Machine 1, lecture number 6. Today we are going to study the counter-electromotive force, acceleration of the motor, mechanical power and torque in machine or motor, and speed of rotation. So first of all, counter-electromotive force. What is counter-electromotive force? We know that a DC motor are built in a similar way as a generator are. Therefore, we can say that a DC machine can operate either as a motor or as a generator. We consider a DC generator in which the armature initially at rest and is connected to a DC source ES by means of a switch. The armature has a resistance R and the magnetic field is created by a set of permanent magnet. When the switch closed, a large current flow in the armature because its resistance is very low. The armature conductors are subjected to a force because they are in magnetic field created by the permanent magnet. We know that whenever a current carrying conductor is placed in a magnetic field, it experiences a force. Now these forces on the armature conductor produce a powerful torque, causing the armature to rotate. When the armature starts to rotate or begin to turn, a second phenomena takes place, that is the generator effect. We know that a voltage E0 is induced in an armature conductor as soon as they cut a magnetic field. We already studied that whenever a conductor moves in a magnetic field, it cuts the flux and EMF induced in it. So the induced voltage is therefore proportional to the speed of rotation N of the motor and the flux per poles, and is given by the equation E0 is equal to flux and Zn by 60. Z is the total number of armature conductor. In the case of motor, the induced voltage is called counter-electromotive force because its polarity always acts against the source voltage E or the supply voltage E. So I am going to summarize it for you people. We have a motor in which there are permanent magnet and we supply the armature through DC power. When we apply power to the stator, it start to rotate and cut the magnetic flux. In this way, EMF induced in the armature, which is opposite to the applied voltage, and we call it back EMF or counter EMF. Now acceleration of the motor. We know that the net voltage acting in the armature circuit is ES minus E0, meaning the supply voltage minus the back EMF. So that will be the net voltage acting in the armature circuit. The resulting armature current is limited only by the armature resistance R and given by the equation I is equal to the armature voltage divided by resistance. Initially, when the motor is at rest, the induced voltage is 0, and so the starting current will be equal to I is equal to ES, mean the supply voltage divided by the resistance. Initially, the starting current may be 20 to 30 times greater than the nominal field load current of the motor. In practice, this would cause the fuse to blow or the circuit breaker to trip. So initially, when the motor is at rest, high current produces because of low resistance, and it is 20 to 30 times greater than the nominal full load current and can cause the fuse to blow or the circuit breaker to trip. We can use a series resistance to minimize this current. Now, as the speed increase, mean when the motor starts, the counter EMF also increase, because we know that it depends on the speed and flux, with the result that the value of ES minus E naught reduces. When the supply voltage is, let's suppose, 200 volt, and by increasing the speed the value of E naught increases, so when suppose E naught become 180, so the resultant voltage will be 20 volts, so mean the ES minus E naught value reduces. It means that the armature current I drop progressively as the speed increases, and when the voltage decreases, the current in the armature also decreases. The motor continues to accelerate until it reaches a definite maximum speed. At no load, this speed produces a counter EMF E slightly less than the source voltage ES. At no load, the peak EMF is slightly less than the source or supply voltage. In effect, if E naught were equal to ES, now suppose a position when E naught become equal to ES, the net voltage ES minus E naught becomes 0, and so too would the current I. The driving force would cease to act on the armature conductor, and the mechanical drag imposed by the fan and the bearing would immediately cause the motor to slow down or stop. In a second scenario, as the speed decreases, the net voltage this increases, and so does the current. The speed will fall as soon as the torque developed by the armature current is equal to the load current. Thus, when a motor runs at no load, the counter EMF must be slightly less than ES, so as to enable a small current to flow sufficient to produce the required torque. So, two main scenarios. The one is the case when the speed increase, the counter EMF E also start to increase, and this resultant voltage in the armature reduces, as well as the current. In the second case, when the speed decreases, the net voltage increases, and so does the current, and the speed will fall. Now let's see an example. The armature of a permanent magnet DC generator has a resistance of 1 ohm and generate a voltage of 50 volt when the speed is 500 revolution per minute. If the armature is connected to a source of 150 volt, calculate the following. Meaning we have an armature and a permanent magnet DC generator has a resistance of 1 ohm and generate a voltage of 50 volt when the speed is 500 rpm. If the armature is connected to a source of 150 volt, we need to calculate the starting current, the counter EMF when the motor runs at 1000 revolution per minute and 460 revolution per minute, the armature current at 1000 revolution per minute and at 460 revolution per minute. So let's start the solution. First we need to find the current I, which is equal to the supply voltage divided by resistance. So 150 volt divided by 1 ohm, we got 150 ampere. The next one is, because the generator voltage is 50 volt at 500 revolution per minute, the counter EMF of the motor will be 100 at 1000 rpm and 146 at 460 revolution per minute. The net voltage in the armature circuit at 100 revolution per minute is ES minus E naught, mean 150 minus 100 is equal to 50 volt, and the current will be equal to I is equal to ES minus E naught is equal to 50 divided by 1 is equal to 50 ampere. We already calculated the 100 E naught, mean the peak EMF at 1000 rpm, that is 100 volt. When the motor speed reach 460 revolution per minute, the counter EMF will be 146 volt, as we discussed here in step number 2, almost equal to the source voltage, that is 150. Under this condition, the armature current is only equal to ES minus E naught by R is equal to 150 minus 146 by 1 is equal to 4 ampere. Now mechanical power and torque in a machine. So let's suppose TA be the torque developed by the armature of a motor running at N revolution per second. If TA is in Newton per meter, then the power developed is equal to TA multiplied by 2 pi n watt. We also know that electrical power converted into mechanical power in armature is the basic principle of the motor. So this is equal to the EV and IA, mean voltage and current watt. So we know by computing these two equations, we get TA multiplied by 2 pi n is equal to EV into IA. Then we already know that the value of back EMF is equal to flux into number of armature conductor and speed multiplied by P by A volt. We have TA multiplied by 2 pi n is equal to, by putting the value of EB in this equation, we got this equation. Now by finding TA, we got this equation. So from this we can see that the torque is directly proportional to the flux and armature current. Now speed of rotation. When a DC motor drives a load between no load and full load, the IR drop due to armature resistance is always small compared to the supply voltage ES. This means that the counter EMF is nearly equal to the supply voltage. On the other hand, we already seen that the E naught or voltage at no load may be expressed by the equation this. So if we replace E naught by the supply voltage, as E naught is nearly equal to the supply voltage Es, we obtain this equation like this, and then we can find the speed n from this equation. So we got n is equal to supply voltage 60 divided by phi by z, phi z. So what it means that the speed of the motor is directly proportional to the armature supply voltage and inversely proportional to the flux per pole, as it's seen that speed is directly proportional to the voltage and inversely proportional to the flux per poles. So thank you. This is all from the today